Hello, this is Jack Jackson. In this playlist, we're going to be doing week 4 of my History of Math class. This is going to be part 2 of our exploration of mathematics in ancient Greece. And basically, we're going to go from the time of Archimedes to the time of Hypatia. So, first up, Archimedes. Before we get into that, let me just briefly mention some of the main sources that I'm using for preparing these lectures. One is the lectures of my friend and former colleague Todd Timmons. Dr. Timmons allowed me to use his slides and so forth for this. Our textbook, A History of Mathematics, an Introduction by Victor J. Katz, and the MacTutor History of Mathematics, online source that I've mentioned before that is very good. A couple other books, Math Makers and Math Through the Ages, and you can see the authors here. I use those and other sources as well, but there's a few of them. So let's talk about Archimedes. Here is an engraving from a book from 1586, much after actually Archimedes lived. So this is, of course, just an artist rendering, but there he is, Archimedes. Archimedes lived from about 287 BCE to 212 BCE, or in other words, if you can just remember the 3rd century BCE, that would be pretty good. He lived in Syracuse on the island of Sicily, which Sicily today is part of Italy. At that point, it was part of the Greek culture. He's undoubtedly the greatest mathematician of antiquity, definitely in the top 10 mathematicians of all time. So if you had to make a list, who are the best mathematicians of all times, he is almost always going to make everybody's list. In fact, and some folks say he is the greatest mathematician of all times, period. Of course, that's a fantastic claim. He has as good a claim to it as anybody does. It's a little hard to compare who's the greatest mathematician when you compare him to some later mathematicians, uh, say Leonard Euler or Carl Gauss, for example, um, because they're very different. They came from very different times. Some of these later mathematicians um, knew a lot more, certainly. Certainly, some students today know many things that Archimedes didn't know about mathematics because they were created, invented, discovered in those centuries between Archimedes and today. Certainly, folks like, say, Gauss or Euler knew much more mathematics. Those are a couple others that are contenders for top mathematician of all times. But think about Archimedes. He was working in antiquity. So little was known. Now his life probably overlapped Euclid's a little bit. Undoubtedly, he knew about the results that Euclid had written in his works. Probably had copies of all of Euclid's works and some others from that time before him. So he wasn't operating in a complete vacuum, but the amount of material that was around before his time was much less. And yet he was able to do some very amazing things. I mean, for goodness sakes, he wasn't even using our modern numeration system. He was using ancient Greek numerals. And so he was able to do so much with that. He studied at Alexandria, Egypt, possibly with Euclid himself, because their lives did probably overlap a little bit, but certainly with Euclid's successors. And we know that he corresponded with mathematicians at Alexandria fairly regularly, sending them letters, sending them his work. He was also known as an inventor and engineer. We'll talk a little bit more about that later. Among the other inventions he invented were the Archimedean screw, compound pulley, levers, and engines of war. Here's a picture of the Archimedean screw, and you can use this to lift, say, lift water out of a well up. And by the way, this device is still in use today in some places. He, even though he was an inventor and an engineer, uh, he definitely was not afraid of getting his hands uh, involved in practical uh, applications of mathematics and science. Nevertheless, he really valued pure mathematics. He was a pure mathematician at heart. He definitely spent time trying to preserve his pure mathematics and not so much about his inventions, even though he was actually known more as an inventor during his time even than a mathematician. Because of his prominence, he is an image on the Fields Medal. There's a picture of the front of the Fields Medal, and that's supposed to be a picture of Archimedes. This is a quote from Archimedes here around this, and the back has some things related to Archimedes as well. The Fields Medal is generally considered the top award in mathematics, at least one of the top two. The Abel Prize is another one. But the Fields, this is sort of the equivalent of like a Nobel Prize in science. Um, so you know the Fields Medal's designers lifted him up as prominence to put him on that medal. So we compare and contrast him with Euclid a little bit. He did not write textbooks like Euclid did. So as if you remember, Euclid had a lot of his stuff, especially the elements, were basically textbooks and compilations of things that other folks had put together. Uh, Perhaps, probably even some of the work was new to Euclid, but most of it probably was not. And but it was there set out as a textbook. In contrast, what Archimedes did is what we would now call research papers. They didn't have academic journals back then like we do today, but it would be like a monograph or something like that. We would call it today. And in these, he sent these to his colleagues in, you know, say in Alexandria and other places. So he lived in Syracuse after he studied in Alexandria for a while, moved back to Syracuse and worked there. But some of these things were in the form of letters, and he did have prefaces to some of these letters. Um, so that's somehow we know about not only what his results were and what the proofs were, but also how he came about some of his methods, and in some cases, who he knew, who he was sending these letters to, um, and some things like that. So you know a little bit about his life from that. In contrast with Euclid, where Euclid's texts are kind of a standalone text, and they're not really say anything really about Euclid himself or about the people he was with. Now remember, all original manuscripts of all Greek mathematical works from this entire period of Greek mathematics, or in fact everything we've studied so far in these playlists and in this class, nothing of that really exists. There are a few things we have that are original things for a few Egyptian papyrus, a few more cuneiform tablets and so forth, but we have nothing like that for the Greeks at all. So everything we have is copies of copies of copies, and sometimes translated, and sometimes with commentaries. So a commentary, we'll talk more about this in later videos, but a commentary is when they will take and copy somebody's early work, but then expound upon it, often adding material to it. The earliest actual original copies we have come from the 6th century CE. So now remember back here, Euclid's from the 3rd century BCE, so like 9 centuries later, then we have uh, that's the first actual physical copies of something that we have that's Archimedes' work. But his work was important enough that we do have several copies of them. Of course, there's always a detective work here for the historians to look at this and see what is actually uh, original to Archimedes that got copied correctly, what might have changed, and so forth. But we have enough things that we're fairly certain we know some things about him. We also know some things about his life. Like I already mentioned, some of the prefaces of his letters. We have that. There's some contemporary historians wrote about him. Plutarch, who wrote about a lot of. He was Roman, talked about some of the Roman history. He had learned something about Archimedes and wrote some things about him in his works too. So we know a few things from there. So we typically know more about his life than other Greeks. He was more famous outside, within the Greek world and without it, outside of it. Um, But we still don't know few details of his life. Unfortunately, there was apparently a contemporaneous biography. One of his friends wrote a biography about him, somebody who actually knew him, but that's been lost. It's kind of too bad. If we had that, we would have known much more about Archimedes and the life of the time and what it was like to be a mathematician at the time. We do have some existing works of his, several here. We have On Plane Equilibriums, 2 books. That talks about, um, here's kind of an idea what some of the things that are in the books, just condensing it down to a few things. So this one talks, among other things, about mechanics, center of gravity, its approach using geometry. Quadrature of the parabola talks about the area of parabola cut off by any chord. On the sphere and cylinder, 2 books, surface areas, volumes cut by a plane to a prescribed ratio. This is what Archimedes, one of his proudest achievements, and wanted this on his tombstone. On spirals, talks about their properties, tangents, and area. Related to that, there's a thing called an Archimedean spiral that's pretty famous. It's talked about in there. On conoids and spheroids, he talks about surfaces of revolution of conics. Okay, on floating bodies, 2 books, hydrostatics. He talks about there. He brings forth something called the Archimedean principle, which gives the weight of a body immersed in a liquid. On measurement of a circle, approximates pi by inscribing and circumscribing regular 96gons. Now notice that is a very calculation intensive endeavor. So he did not shy away from calculations at all. So he's much more likely to be actually dealing with numbers and calculations than say you're going to find in the elements, for example. The Sandra Connor proposes a new number system that will handle large numbers. Didn't really catch on, but he had a system there. The method includes descriptions of how he found results, and they were kind of a heuristic arguments or maybe a mechanical argument or approach to find the result, but then he later followed it up by a proof. Of course, it was Greek, so it was a geometric style proof. Now, there are several works that he probably did that we've lost on balances and levers, on semi-regular polyhedra, something on mirrors, and perhaps others. I want to talk a minute about the method because the method is really interesting. It was only discovered in 1899, previously had been lost, and it's what's been known as the Archimedes Palimpsest. Now, let me explain what this is. You can see a picture of it right here. And so this is on a parchment. Now, of course, this is not Archimedes' original handwriting or anything like that. This is going to be a copy of a copy. There were copies later on. But what happened is this Archimedes' work was copied and was written on this parchment. Now, what happened is paper parchment was hard to come by. So actually what happened is somewhere in the 13th century, somebody found this parchment with this mathematics on it. They didn't care about the mathematics, so they kind of tried to scrape off the mathematics, scrape off the writing, basically took an eraser to it and put some chemical on there to try to clean off the writing, and then they wrote over it with what they wanted, which in this case was Christian prayers. And there were 7 Archimedes print treatises. So I think originally probably this is parchment going this way with the writing going up and down this way, and then that was kind of scraped off, kind of cut into or bound into, and made into a book. And so it's a prayer book. And so it's a long story that you can read about if you'll look it up. But basically, that through a long series of events, this book was finally found, and they noticed that there looked like there was some mathematics there underneath it, some geometric figures, maybe some mathematical writing. You can kind of see it going across there underneath the prayer books. Thankfully, they weren't very good about completely scraping and cleaning it off before they wrote the new prayers over it. So eventually, this has made it to where we try to look and see what's there. Well, now some of this writing was barely legible, and we're using modern techniques to bring out the rest. So here you see a piece of it put down here, and I'm not even sure what all they're doing here, looking at it through microscopes, maybe exposing it to some different kinds of lighting, maybe even some, uh, I don't know what all they're doing here. So they're using modern technology to look into this, and so they could take something, say, that looks like this in the middle picture, and there it is in the right picture, and now we can see much more of the mathematics that's underneath. I think it was the same thing on the yeah, here it is again, a different picture of the same basic part of it. Of course, that's just one piece of the whole thing. So it's pretty amazing. Here's some more here, where maybe here was the original, and here is what they're able to do to look at it with, I don't know if they're applying X-rays or whatever they're doing, but anyway, somehow or another, um, they're able to look at this with different kind, probably not X-rays, but they're probably looking at it with different kind of lights and so forth. So in any event, yeah, pretty fascinating stuff that they're able to take these artifacts, and then now we know about the works and the method. And the method we we actually describes his method of doing things in some cases. So we know a lot more about Archimedes now that we actually have access to this work. What are some of the things that Archimedes did? Well, one of the things he's best known for is applying Eudoxus's method of exhaustion to prove many theorems, including finding and proving new area and volume formulas. And if you notice, this Eudoxus and especially Archimedes here really foreshadowed calculus a lot. This is a lot like integral calculus. So in some sense, we definitely have some sense of a limit idea, even though they didn't phrase it in those terms, going all the way back here to Eudoxus and Archimedes. So, the roots of calculus go quite far back there. He gave the first known rigorous bounds on pi. He said pi was greater than 3 and 1071st and less than 3 and 1/7. 3 and 1/7 is also 22 sevenths. So 22 sevenths is a common approximation for pi. But he realized that 22 sevenths or 3 and 1071st both were not really correct values of pi. He knew that pi was something between those two, but he knew that they were approximations. If you average those two bounds, those two bounds roughly work out to be about 3.1408 to 3.1429, so it's something in between there. And if you average those two, you get 3 and 141,994, so approximately 3.14185, which we know now agrees to pi to about 4 significant digits. So that's a pretty good approximation of pi, considering where he was in time. Definitely a lot better than 3.14. At least it picks up another digit of accuracy. But more importantly, he also knew that this was an approximation. So he didn't say this was pi. He gave rigorous bounds and proved that pi was between those. And like I said before, this used inscribing and circumscribing regular 96gons inside and outside of a circle, so that basically he's actually computing the area of those figures, and that is very, very intensive calculations. So notice that he did not shy away from complex calculations. He also applied mathematics to physics and engineering. And here's a quote that's in our textbook. Archimedes was the first mathematician to derive quantitative results from the creation of mathematical models of physical problems on the Earth. So he used mathematical modeling, where he gave a physical problem and gave sort of an idealized version of it. And in CATS, it talks about, for example, he's talking about the lever, and he works with an idealized lever where the lever itself couldn't bend, break, and didn't have any mass. So that has it's an idealized version of that. So it's a model, but the physical reality, approximates that model, or the model approximates the physical reality. Here's some interesting quotes. This one's by Archimedes himself from the method, now that we were able to to read that palimpsest and see it. Certain things first became clear to me by a mechanical method, although they had to be proved by geometry afterwards, because their investigation by the said method did not furnish an actual proof. But it is of course easier when we have previously acquired by the method some knowledge of the questions to supply the proof than it is to find it without any previous knowledge. That's Archimedes from the method. I got that quote via MacTutor. So notice what he's saying here. He's saying that he's explaining how he found some of his results, and in some of his letters that he wrote, the first part will explain kind of how he went about his results, followed by some of the actual results and then the proofs. But he knew he had to give a rigorous proof. And of course, with the Greeks, the rigorous proof was geometric in nature, even though the way he found the result may have been more arithmetic or mechanical, or even just some kind of heuristic argument. Here is a quote by Plutarch, again via MacTutor. Plutarch was a historian of contemporaneous with Archimedes. It is not possible to find in all geometry more difficult and intrinsic questions, or more simple and lucid explanations. Some ascribe this to his natural genius, while others think that incredible effort and toil produced these, to all appearances, easy and labored results. Yet no amount of investigation of yours would succeed in attaining the proof, and yet, once seen, you immediately believe you would have discovered it by so smooth and so rapid a path he leads you to the conclusion required. So basically, he's saying there that some of the results that he found, had you been alive at the time and were trying to find him, that probably not just you, anybody would have not found it. After all, we're saying he is probably the greatest mathematician of all times, or one of them for sure. And yet, he was so good at writing that up and making it clear that once you see how he did it, it just seems like, yeah, that's a pretty natural thing to do. And you can understand how he got his results. One of the most things that quotes that he's most famous for is yelling "Eureka! Eureka! I found," which translates as "I found it! I found it!" And the story that goes with that is that he was given a crown by the ruler there in Syracuse, and he suspected that it had been substituted with a cheaper metal, at least a portion of it, and the story goes is that he was in a bathtub and looked at the water displaced by his body and realized that the water displaced by the crown could have something to do with its weight, and he was able to use that to maybe figure that out. And once he realized this, he jumped up naked, running through the streets, yelling, "I found it! I found it!" Actually, it's interesting of some stories about him, taking a bath. He often even would not take a bath. That he would get so involved in his studies that he would neglect his hygiene a little bit, and his colleagues would, I guess, and family members, I guess, would maybe force him to go take a bath. He was so involved in what he was doing. So what are some of the things he worked on? Well, he also worked on a lot of mechanical inventions. We already mentioned the Archimedean screw. He also worked a lot on lever. Not only did he I don't know if he invented the lever, but he gave an explanation and proof of its use and its properties. And he's also been able to move heavy weights with a pulley. He was once claimed to have said that, give me a lever long enough and a fulcrum to place it on, and I can move the entire earth. Okay, or and apparently one of the stories goes that the ruler kind of challenged him to sort of back that up with actuality, maybe not moving the earth, but moving something large, and he was able to, probably more with pulleys than with levers, able to move a large ship by gaining a large mechanical advantage on a pulley and move that. So he was able to do very practical things. And one of the things that probably he was most famous for were his inventions, and particularly some of his engines of war. So in 1212 BCE, and probably before that as well, the The Romans, which are just right next door there to Sicily where he was, in Syracuse, they were trying to take over Syracuse. And uh, Archimedes used his mechanical genius to develop some engines of war uh, to keep the basically keep the Roman navy away from the shore, and things that would throw projectiles and different things out there to keep them away, and they were very very effective. And there's a couple of versions of the story of his death, but eventually, but here's sort of one version, is that in 1212 BCE, the Romans finally overcame them in spite of his engines of war, which kept them away for quite some time. They were just finally, the Syracuse folks were just finally overpowered by the Roman navy and army. And the Roman commander actually had specific orders to take Archimedes alive. But the story goes is there was a soldier that came upon him, and Archimedes was working on some math problems, and he was drawing circles in the sand and thinking about a problem. And he basically told the guy, "Leave my circles alone. Get out of my light. Get out of my way. Don't disturb my circles." And the Roman actually ended up killing him. The Roman, the guy that killed him, probably got himself killed as well because he wasn't supposed to do that. So eventually, here's another version of a picture of him. And eventually, of course, he was died then, and he was buried. On his tombstone, he got his request of putting a cylinder enclosing a sphere there as well. So there we go. Archimedes of Syracuse, one of, if not the greatest mathematician of all times.